welcome. My name is Professor Andy Gooden from University of Southampton, one of the co-directors for the energy storage of CDT energy studies and its applications. Clearly, there's something wrong with that side of the room, but that side. Okay, so it's my pleasure to welcome you to this multi-CDT conference in clean energy and sustainable infrastructure. Now, quite unique and probably something we should have done some time ago, possibly rather than having our individual CDT conferences. It would make sense, I think, to have done this a bit earlier. However, we have 3 CDTs present with energy storage and its applications, new and sustainable PV, and sustainable infrastructure systems. It works. Well, I'm waiting for that. I should also say welcome to our global audience that are live streaming. Okay, so I thought I'd start with just something we should all be aware of is what the CDTs were set up for. So again, principally they were set up to train the research leaders of the future. That's the focus of CDTs we have represented. Again, I just thought I'd put up brief statements taken from their individual focuses on the different technology areas. So again, I think we have collectively the context for clean energy and sustainable systems. Again, we are bang on trend. There's never been a more important moment in terms of the work that we're collectively doing. Obviously, back in October last year, just before the COP26, we had the government strategy on net zero. Again, recently there has been much press news about the cost of energy, and again, our energy security, or rather insecurity just now, and how we need to try and transition. Again, electric vehicles, so dealing both with energy storage, again with infrastructure. Again, there was a recent new national infrastructure for EV charging, just published on the 25th of March. So all this is happening now, and this is all in the lead up to this Thursday. Again, a part of the government is going to publish its new energy strategy. There's going to be a focus on nuclear and renewables and what else. So again, clearly we are bang on trend. We are trying to address these major societal challenges. I can't remember if I've just advanced 2 or 1. No, I haven't. Okay, so again, in terms of outputs, the CDTs themselves, so these were the 2013, 2014 generation of CDTs, are now coming towards their end. So we now have a number of very tangible outputs. Clearly, the main thing is students in terms of numbers we've recruited and numbers graduating up there. A whole host of publications and other outputs, some of which I'll detail in just a minute, across sites for the various CDTs. So again, substantial recruitment and progress across the various CDTs. In terms of publication, I just want to flag that this multi-CDT conference will be published. So again, the proceedings will be open access available. It will be available for all time. Again, and that follows a trend that we started in the energy storage one of, again, publishing our proceedings as a tangible and long-lasting output, research output from the CDTs. Training. Clearly, the 3 individual CDTs have developed and delivered the training programs across these technology areas. They still exist, although clearly we're not progressing students through those training programs now. But again, that work is there and can still be used. We have supported work and industry placements across the CDTs as well, and that's important to make sure that we're engaging with industry to then be able to deliver the output of our research. We have provided evidence and input to a number of policy calls, with calls for evidence and consultations from government across a wide range of relevant areas. And again, that's important that we use our expertise to feed into that. We just showed earlier the number of policy and new strategies that are coming out for government, and that helps inform where that money should be invested in. And we've also supported a number of technical visits and international workshops and trips around the world. Again, that's important from a networking point of view, both in terms of learning what other people are doing, but also telling other people what we're doing and networking. Again, that's a crucial part of the training element of this, is to build up your peer networks across the globe. And again, outreach. So the various CDTs have all engaged in different forms of outreach. The energy storage one, again, there's two activities that we've been leading on. One was an energy storage game, if you like, for schools, and one was looking at, for an event for different conferences and festivals, looking at how we process, and you could physically have a go at reprocessing some batteries and recovering the materials. Again, CDT SIS done a number of things. This was one of the more recent ones. They demonstrated this FIS passage run at the Winchester Science Centre, again, but as part of World Environment Day. So again, engaging in these type of events and showcasing the output of the various CDT. Again, have delivered workshop sessions again in terms of engaging with schools, looking at that particular school was seeking to be a solar school. And again, therefore, it's highly relevant that the PV one. And again, they've held a number of open showcase events that were open to the public. Tracy and both thank Tracy and Jerry in particular for helping in organising this and bringing this together. And just before I hand over, again, in terms of housekeeping, so I'm led to believe there are no planned fire alarms today. Tomorrow morning, there might be one, but today, if it goes off, we need to treat that seriously. Exit out there, up the stairs and out the front of the building and into the grass area in front of the church. Toilets are out the main door on the left-hand side, and clearly we have a programme of breaks as well. So, first of all, thank you all for attending and contributing to conferences. Again, let's make this a successful event in terms of conversation across these different technology areas, which clearly under a clean energy and sustainable systems have a very clear focus on those technology areas. I'm going to hand over now, as we have done in the past, we then work our students. So we're going to get the students to chair the various sessions. I'm going to hand over now to Bernd and Ben to chair our next session. So thank you very much.
Yeah, so the first talk, the first keynote.
Morning, William. Can you hear us?
Hi, yes, I can hear you.
Excellent. Excellent. Okay, so we're just getting the technology to work. Are you ready and able to present?
Am I going to share my screen? Are we going to run it from there?
Yes, you're going to share your screen.
Okay, that's fine.
And I'm guessing that you're able to and willing to take questions either during it or after it. William, which would you prefer?
Probably if I run through it and then we do it afterwards, that would be good.
Okay.
Okay, it's fairly brief, I think. although it depends how much I go wibbling on. So the idea is, anyway, okay, I'll get going. Okay, well, good morning to everybody. I'm sorry I can't be there in person, but I've kind of, I think one of the sort of difficult things about getting back to going places is that we're sort of used to having 5 minutes between meetings, which are very often in different physical locations. So unfortunately, I've got a bit of university stuff that I've got to do this afternoon and tomorrow, which meant that it wasn't really possible to come up and join you. But I hope you all have a great conference. And listening to Andy's opening session, it sounds like it's got off to a great start, and it's hopefully a celebration of what has been achieved. So I'm William Parry. I'm a Professor of Geotechnical Engineering at the University of Southampton. With Paul Kemp and Jenny, I lead the CDT CIS. I'm also the convener of a thing called UCRIC, which is the UK Collaboratorium for Research in Infrastructure and Cities. And I'm a member of the DFT Science Advisory Council, but what I'm going to be saying these are my own views. I have to make that completely clear. I've called it a provocation because what I hope it will do is provoke a debate rather than a punch in the face, which you can't do because I'm not there, but I'm sure you wouldn't anyway. So hopefully we'll have a bit of time for some questions and comments afterwards. So it's a series of thoughts, really, thinking about what is the future of mobility going to be like. And that really was a topic that I've chosen deliberately to try and be at the nexus. So it hopefully is of some relevance to all of the CDTs. Okay, right, let's see if I can get a page down. Okay, right, okay, there we go. Okay, so the future. So here's a couple of thoughts about the future. It's tough to make predictions, especially about the future, which is attributed to various people, but the person I think probably said it was Yogi Berra. So basically try to avoid predictions, especially about the future. Here's another one, which is the author William Gibson. The future is already here. It's just not very evenly distributed. So that one's a little bit old hat now. But the one thing that we do know is that unless we do something pretty quick, we are heading towards an environmental catastrophe. I might have said 2 environmental catastrophes. One of them is climate, and that's one of the reasons why there is the emphasis on net zero. But there is another environmental catastrophe, not unrelated, which is loss of biodiversity. So we really do need to act now. And it's interesting that the current so-called cost of living crisis, which when I was younger would have just been called inflation, essentially has really thrown into stark contrast that when it comes to a choice between the environment, climate change, and upping the thermostat by a few degrees, we very quickly reverted to upping the thermostat by a few degrees and paying a few dollars more to dodgy nations for their fossil fuel. And I think it is disappointing that in a sense, the world has failed the first real test of how are we going to tackle climate change through changing our habits and patterns of energy use. So this is the future that we know faces us. And actually, harking back to William Gibson, some of it is already here some of the time. So this is really what we need to avert. So when we perhaps try to go into sort of predicting the future, autonomy, so this is the future in terms of transport now, autonomy is probably going to play a big role, but I think most experts in the field feel that it's probably a little bit further away than government might like to think. We have some other apparent choices, but I don't think they're real choices because I think the future is actually going to be a little bit of everything. So will we have individual pods or will we have things joined up into a train, whether that's a platoon of road vehicles or a traditional train or both, doesn't really matter. So it's individual pod versus a train of pods. Then on the top right here, we've got what's the source of energy or power going to be? So unmotored, walking, wheeling, cycling, battery, electric connected to overhead wires. Will it be hydrogen? Will it be some sort of biofuel? So, all of those are kind of in the mix. And too often, I think we see these as competing modes, whereas I think what I hope to show is in reality, we're going to need all of these sources of energy for our future mobility. And then there is another quite big debate, which nobody has really said very much about, is what's the future of private vehicle ownership versus public or shared vehicle ownership? And I think that's something which has got an important part to play in our future of mobility. So the concerns that we might have are then, where's the energy going to come from? Where are the raw materials going to come from? What is the effect of and on climate change, and how do we avert that? It's not actually only climate change, there are also environmental pollution issues, possibly contributing to the loss of biodiversity, and also the environmental pollution and other issues contribute to human health and well-being. So all of these things need to be taken into the mix. So we'll have a look at all of those today. So sources of energy, so these are just in alphabetical order. So we might have ammonia, biomass or bioethanol or methane from the anaerobic digestion of waste. Electricity could come from a national grid, it could come from a regional or a local grid. Both of those need some sort of infrastructure. It could come from batteries, and the batteries need materials. It could come from glycerol, which is currently a waste from biodiesel production. It could just be human energy from walking, wheeling and cycling. We could be looking, I know this is one of, Andy's just got a big program grant in this area, and this is basically about energy storage technology, which would decouple electrical vehicle supply from the grid. So basically you could generate the electricity from renewable sources, store it locally, and then put it straight into vehicles. And that has some huge benefits because there is no need for a grid connection, which currently it's the need for a grid connection, which makes some marginal renewable schemes unaffordable. And then of course there is hydrogen. And the big question with hydrogen is, where do you get it from? And if it's from a hydrocarbon, then obviously you're into the whole business of fossil hydrocarbon, you're into the whole business of carbon sequestration and storage. If on the other hand, it is made using renewable electricity, then actually it probably is better to try to use that electricity directly. And the circumstances where you would be wanting to use hydrogen are probably fairly limited. Maybe you would make it in a depot, a bus depot or a train depot and use it locally. And the big advantage is probably to avoid having lots and lots of grid infrastructure. So, okay, just as an example of those, let's have a look at the availability of biofuels. So early biofuels come from crops, and that's an interesting thought when a lot of the world goes hungry. But then if you're clever about it, you can make it so that you use bits of the crops that are not edible, but you can use those to make biofuels. There's a series of what we might call second generation biofuels. So hydroprocessed esters and fatty acids, wood processing, forestry, agricultural, municipal solid waste and so on. And then third generation or future fuels, possibly from algae, sometimes known in the press as bionic duckweed and semi-arable land. But the point about this is that if you add up all of those likely sources, you get something like 625 megatons per annum of available biofuel. And that's your lot. And other than that, you're sort of into then using land and biomass, which we currently use for other more important things like eating. So there is a finite availability of biofuel. So if the total fuel is about 600 megatons per year, suppose the energy density of the biofuel is about 40 gigajoules per ton, then we can work out the total biofuel energy available, which is 600 times 40, which is roughly 24 exajoules per year. And an exajoule is 10 to the 18 joules. And to put that in the context of sort of electricity generation, it's about 2.8 times 10 to the 5 gigawatt hours. This all gets it's quite easy to get quite confused with the powers of 10 and all the rest of it. But just bear in mind that 24 exajoules for now. So actually, when we look at the current energy demand, which is shown in the table here, we have high energy demand industries, manufacturing steel, cement and aluminium. We have a lot in transport, light duty, heavy duty, shipping and aviation. We use an awful lot of energy for space and water heating and then to power devices. So our total energy demand is about 614 exajoules per year. The interesting thing with the 24 exajoules per year we can get from biofuels is that aviation uses all of it. So it does not go a terribly long way in terms of satisfying current energy use. Now, of course, aviation is probably one of the most difficult forms of transport because you have to carry the fuel with you and there is a huge weight penalty. So you don't really want to be carrying heavy things as batteries have traditionally been. Hydrogen is a problem, not because of its energy density per unit mass, but because of the challenges of getting it into a sensible volume. But the way that we're going with motor vehicles, with road vehicles, with land vehicles is very much about towards electric or at least hybrid cars. And this morning I heard on the radio that apparently sales of electric cars in the past year have been greater than the total of data in the past month, or greater than the previous year or something like that. So there's no doubt that hybrid and battery cars are very definitely taking off. But we also need to think about the role of public transport and of rail. So rail in particular is currently really the only mode that offers zero CO2 emissions at the point of view, certainly of mass transport. The battery car will do that, but there are still concerns, I suppose, about range and availability. But also the steel wheel on the steel rail is very low friction, it's got a very low rolling resistance. And when we look at, these are just from publicly available data, a Pendolino train uses an average of 23 watt-hours per seat kilometre at a speed of about 200 kilometres per hour. An electric car, battery-operated car, is about twice that, at about half the speed. So there is that huge efficiency advantage of running a railway, which means that you're losing much less in rolling resistance than with rubber tyres on tarmac. But it's not just about CO2, because there are other emissions that come from road transport, in particular the particulates that we generate. I'll come back to the particulates in a minute. Currently, the modal split for inland surface transport, or certainly pre-pandemic, was about 90% road, 10% rail. I suspect it's got worse. So the challenge for rail is that a shift of 10% from road would double current rail journeys. And this is at a time when basically the rail network is already fuller and busier than at any time in the last 60 years. That was true pre-pandemic. Post-pandemic, it's probably not quite operating at that capacity, so it does need to get itself back. Post-pandemic, I think there are also opportunities for rail freight, and that would be something that we should look at in an integrated transport policy. But undoubtedly, the challenge for rail is to generate and accommodate the modal shift. So I said that it wasn't just about CO2. So these are a couple of press cuttings attributing the global number of deaths to outdoor air pollution. A lot of that air pollution comes from transport, and it's very often not road transport in particular. It's very often not just CO2, it's particulates. So yes, particulates from diesel emissions, that can be overcome to some extent by filtration. That would be overcome by a move to battery cars. But what you won't overcome is the dust generated by the wear of the tyres on the tarmac, brake wear, and all the rest of it. So again, these are some more press cuttings. So road transport is estimated to be responsible for about 50% of total nitrogen dioxide emissions. And then we see here that on the M60, one of the reasons for scaling back plans for hard shoulder running, one of the reasons that they quite often impose speed limits now is to reduce pollution from road vehicles. So even moving to battery vehicles will not tackle the emissions which are associated with wear from the tyres and the tarmac. One of the issues with rail electrification is that it requires infrastructure, and some of you will be aware of the Great Western Electrification Programme, which went massively over budget and in the end ended up being very curtailed. And we sort of lost the ability to design and construct economically viable electrification infrastructure. The rail industry has, I think, begun to get that back, and so more recent schemes have been restarted. So this actually led to a pause in electrification, which was not a sensible thing to do. But when you look at that forest of gantries and think about the amount of steel involved, you do realise that actually electrification infrastructure, we have got to find ways of making that not only more affordable, but more efficient in terms of materials and, of course, embedded carbon terms. So what about electricity? So the largest wind turbine, which is currently a prototype, it's got 108-metre long blades, and that has a maximum power output of 15 megawatts. So if we say, well, actually, suppose that it operates on average at 50% of its capacity, it would then produce about 70 gigawatts per year. So we'd need 40,000 of those to produce 1 exajoule over a year. And think back to the 24 exajoules of energy that we need for aviation, the 24 exajoules that we could get from biofuels, and the 600 or so exajoules that we need. So that's an awful lot of wind turbines. So there's got to be a question about whether it's actually viable to generate the electricity that we would need to replace current usage. And it's not just about the logistics of providing the infrastructure. We need to think about materials. So if we're talking about batteries, lithium, cobalt, if we're talking about, for example, rail electrification infrastructure, copper, steel, aluminium are all going to be important. And I'm just going to have a quick look at steel. So this is taken from a great book by Julian Allwood and his colleague called Sustainable Materials Without the Hot Air. And this shows how basically this is the steel stocks in circulation in a developed society and how it rises with GDP and plateaus out at somewhere probably about 10 or 11 tons of steel per person. And if we look at the world iron reserves and the world population, what we will see is that there is barely 10 tons per person. So if the whole planet gets up to the same level of steel usage as a developed country, there is not going to be enough steel to do that. So we need to do something a bit cleverer. Rinse and repeat this for other materials. Sometimes, I think there was a lot of excitement about whether we would run out of, I think it was iridium for a traditional television screen. Then the technology changed and we suddenly didn't need iridium anymore. So it ceased to be a problem. Those jumps in technology do sometimes happen, but we do need to think about how feasible is it to roll out, to scale up the sort of technology that we've already got. And I think just this simple example of iron and steel shows that it probably isn't, and we have to do something a little bit cleverer. So now let's come to active travel. So walking, wheeling and cycling. So my attention was drawn a couple of days ago to this study, which is actually a few years old. So it's a study based on 250,000 people over 5 years. And they found that cycling to work, so basically this is a half-hour cycle commute or whatever, most days cycling to work. And over 5 years, cycling to work versus sitting on a bus, sitting in your car, was associated with a 41% lower risk of dying, 46% lower risk of developing heart disease, 45% lower risk of developing cancer. Now, interestingly, one of the government's headline objectives is 5 years more healthy life for everybody. Admittedly, that was pre-COVID. And there is also a statistic, which is that every minute you spend on a bicycle prolongs your life expectancy by a minute. And when you hear that, you think that can't possibly be true because you'd live forever. It doesn't really work like that. So a half-hour a day commute for 5 days a week each way would get you about another 2.5 years over a 40-year working life. So actually, if you add in a bit of sort of childhood and pre-working cycling and university cycling, and you also factor in that if we had more people cycling, we'd have fewer cars. So you would reduce a few cyclist deaths because they wouldn't be hit by cars. Providing good infrastructure to enable them to do that, also reducing cars would improve air quality. You could probably actually get to that 5 years extra healthy life simply by providing infrastructure that successfully encouraged more of the population to cycle to work. Walking is good, but it's not as good as cycling. Cycling is just that, probably you do that extra distance, it's that extra exercise. So it's no pills, no potions, no fantastic advances in medical sciences. It's just a healthy, active life as part of your daily routine in a healthy environment that isn't all cluttered up with pollution. Okay, so what would be the infrastructure requirements for active travel? So the picture on the top shows a modern Mini on the left versus a traditional Mini. And there was a great graphic that I was been unable to find recently, which actually does a similar thing for lots and lots of modern cars. Generally, there's been a 30% increase in the size of motor vehicles over the last 30, 40 years. There's also a huge amount more traffic. And with the exception of motorways, that's still pretty much squeezed onto the same roads. So the problem is that space for walking and cycling has been squeezed off the roads, with the result that many people now feel that it's dangerous. So we do need to take providing safe infrastructure for walking, cycling and wheeling seriously. We also actually need to include micro-mobility. Where do e-scooters go? Because cars don't really want them on the road. People certainly don't want them on the pavement. And in fact, they're illegal, except in certain test areas at the moment. There is another huge benefit that if we could move towards mobility as a service, we could reduce private vehicle ownership. That would reduce the number of vehicles in circulation, and we wouldn't need to clog up our streets with 2 lanes of car parking. So this is a fairly typical suburban street on the bottom right, and you can see that it's a linear car park with one lane of traffic. We also have got multi-story car parks, underground car parks, and that kind of thing. So imagine you just dialed up a pod when you needed it, and you jumped in and used it, and it didn't have to spend 90% of its life on your drive, on the road, in the garage. That is a huge benefit, because all of that is space that can be freed up for walking, cycling, and actually just making green space that improves people's well-being. Okay, what about White Van Man, all those little deliveries that we had? So it's just a little bit of a video here, which is provided by my colleague Tom Cherritt. They did some work where they looked at 2 companies from 18 vehicles, 3 depots, 1 day. Okay, so this is 2 rival companies, and we're going to track 18 vehicles. They're based at 3 depots. It's over a day. There's a tracker on the vehicle, which is the squares, and the tracker on the driver is a circle. And when the trace becomes more intense, that represents overlap of activity. So we just hopefully play the video. So you can see that they zip in from outside, and then they stop, and then they deliver the rest of the package. So you can see there the 2 companies with the 2 different colors. And this is during the course of the day. We can see this is so this is your Amazon delivery. This is your DPD delivery. This is all of those deliveries that we now rely on when we buy something from the internet. Okay, so you can see the pattern sort of developing. So one of the interesting things is that the area covered by each vehicle is actually not that great, certainly in an urban setting. So that makes you start to think, well, do we actually need the white van? Anyway, you get the picture. So I'll stop the video there. So the average courier was delivering 127 parcels to 72 different consignees, making 37 vehicle stops. And interestingly, they were walking nearly 8 kilometers. So that's 30% nearly of the total journey distance. And the vehicle was stationary on the street for 4.6 hours. So there's got to be a better way of doing this, possibly with joining up, having out of town delivery things, maybe electric cars that do that last mile delivery. So there is certainly a better way of doing that. Okay, so more thoughts about the future. I can cope with the present and plan for the future, but the past will always haunt me. And the reason for that is that you cannot change the past. That was very eloquently put by the poet, or the mathematician actually, Omar Khayyam in his Rubaiyat. So the moving finger writes, and having writ moves on, nor all thy piety nor wit shall lure it back to cancel half a line, nor all thy tears wash out a word of it. And of course, the thing is that today's future is tomorrow's past. And that's why we need to plan for the future and try to get it right. This is me. It's sometimes easier to create the future than predict it. So why sit on your hands worrying about the future, what the future is going to bring? Why not, know what the future needs to look like and make it happen? And I do believe that in the world of transport and mobility, we're in a position to do that, because we do know what the future will bring unless we get this problem sorted. It will bring environmental catastrophe through climate change and loss of biodiversity. So we need a transport hierarchy. So some of you may be familiar with the waste hierarchy, which is that you should avoid waste. If you do create waste, you should reuse it. If you can't reuse it, you should recycle it. If you can't recycle it, you should recover something from it, and only as a last resort would you dispose of it. This is Transport Scotland's national transport strategy. It's got walking and wheeling, and then cycling at the top, public transport, taxis and shared transport, and private car at the bottom. Maybe a difficult political sell in a nation such as, maybe especially England, with its love affair with the private car as an extension of private space. But I do believe that something like this has got to be absolutely at the core of what then follows in terms of a technological strategy. So what would that involve doing? You need good infrastructure. to encourage active transport, walking, wheeling and cycling. There are the direct health benefits that we've already seen, additional health benefits through clean air, through fewer cars, and additional benefits through less likelihood of being killed by a collision with a car. We do need to accommodate micro-mobility, so e-scooters and e-bikes. We need to invest in rail, which is already a low carbon form of transport, to provide capacity for modal shift. We do need to go electric in cities. I think we should only have electric vehicles, ideally buses, trams, trains, but possibly bikes, scooters, delivery vehicles, and then personal mobility for those who need them. You know, in a city, there is really no need to have a privately owned motor vehicle. We should make public transport affordable. So why on earth did a government which professes to the agenda of net zero and levelling up, why did they take 5p off the fuel duty, of which less than half has been passed on to the consumer? Why didn't they reduce bus fares and train fares? Why do we have a system that puts train fares up by inflation plus X% and has done for the last 20 years when fuel duty has been frozen? It makes no sense, and it is certainly not consistent with the stated ambition of net zero. We do need to retain the benefits of home working, and that if we could get away from these peaks in the morning and the evening that we had before the pandemic, then we don't have to size our infrastructure for just a small amount of time during the day. We can try to even out demand during the day. There's a lot we can do, I think, to coordinate those deliveries, for example, out of town distribution hubs. That's the white van video. We do, I think, need to start to discourage individual car ownership, especially in towns and cities. And that does mean that we need to provide public transport options, affordable transport options. It will free up space for recreational use. It will make people feel better with that green space. And we need to move towards the availability of dial-up pods or the equivalent. It might initially be a car that's delivered to your door when you need it. I think we need to prioritize scarce biofuel resources for use where there's no reasonable alternative. So possibly aviation and maybe road freight that we haven't succeeded in displacing to rail. Batteries, I think, have got a clear role. It's already here. We know that. That bit of the future is already with us. And if we do that, I think we can decongest our cities, decarbonize, depollute, declutter, and make space for people. But there's got to be a will, okay? And we can move away from this. So this was the last overseas trip I did before the pandemic. That's Beijing on a Sunday in late October. Or this, which is, again, in China. So this is the Netherlands, where they have deliberately moved to encourage walking and especially cycling over the last 2 decades, or a vision of the future which has got green space and cycle lanes and pedestrian spaces. But it needs 3 things. It needs scientific argument, which I think is there. I think the evidence is all there. It needs political will, which I think is not really quite there. And then you do need to win people's hearts and minds. If you think about some of the great things that have worked, wearing seatbelts, no smoking in pubs, drink driving, all of that was, yes, it was legislation, but it was legislation that was preceded by very strong public awareness campaigns. The one that hasn't really landed is not using your mobile phone while driving, which actually is just as important. It's a dangerous thing to do, but we never really did that public education thing. So actually getting the public on board is just as essential. So it's not just about engineering. It's actually about political science, social science, and getting people on board. But if we have the will, then I believe it could be made to happen. Okay, that's it. So that's it on the slides. So if we have any time for questions and discussion, we can do that.
William, for the very inspiring talk. The microphone for questions. Yes. Oh, perfect. Yes, Jacob.
Hello. Okay. So your talk seemed to mostly focus on sort of domestic travel. I wondered if you had any perspective on sort of international travel and freight.
Yes. Okay. So I mean, I did mention aviation briefly, and that would be the international angle. I suspect that we probably do need to think fairly carefully about our, I would be the last person to say we shouldn't fly. My son actually is a pilot for British Airways, so, maybe that's a question of do as I say, not as I do. I think being able to fly and being able to go places is actually an important part of modern life. But what we maybe need to do is, I think some of what we will have to do is use travel responsibly. So the days of sort of jetting off to Prague for a weekend because you can and because it's cheap, I think possibly we need to look at that. But certainly I think if we could find ways of, and like I think I did say at the end, prioritizing the biofuel as a sort of sustainable aviation fuel, I think would be a good thing to do. But I think we do need to look at our use of travel. Certainly, I feel that over the last pre-pandemic, I would not infrequently, not hugely often, but there were a couple of occasions where I would be invited to fly out to China for a weekend conference, do a keynote talk and fly back. I never liked doing that. And when I was invited, I always tried to take in 2 or 3 other things while I was out there and go out there for a week. And the one occasion where it did look as if it would be out for the weekend, I did decline. I know some of my colleagues have a stronger stance and some of them won't fly at all, which I think actually gets a little bit limiting. So I think it's about responsible use. It's about trying to encourage people to sort of personally prioritize. And then I think as a matter of strategy, we need to think about, where do we use these sustainable biofuels, the high density hydrocarbon fuels? And, I think air travel has got to be the top priority for that. In terms of others, maritime gets a bit of a bad press, but that's mainly, I think, because they tend to use dirty diesel and dirty diesel engines. I know that I've got colleagues who've sort of looked at possibly harnessing wind power or solar power, and again, autonomous vehicles. But transporting something by water is also very, very energy efficient. You go at slow speed, and I don't think, people say shipping is responsible for X% of all CO2 emissions. That's mainly because there's a huge amount of it. And in a per ton way, it's not that great. And I think actually, just finally on this, there is a huge opportunity to make more use of shipping, both around the coast and for sort of international short distance and long distance travel for goods which are not time sensitive. And I think we should make more use of that. So for things that are not time sensitive, to try to get them shipped by water in a sustainable way is also an important part of the strategy.
Hi, thank you very much for your talk. It was really interesting. And although I think we have a great deal to be worried about, I think there's a great deal of hope there as well. Actually, on the just I guess a follow up a bit from Jacob's question on international travel. I'm a bit of a train fan myself, and I was quite interested about some of the plans that China has, for example, to do long distance rail travel with the Belt and Road Initiative, and as a kind of intermediate between flying and shipping that you mentioned. So I was wondering if you had any particular comments on that, and whether you see that becoming more dominant in the next decades.
Yeah, I do. I mean, it is interesting. Sort of, you go back. I don't know whether can I put my video on. That might be a bit nice. Well, it might not be very nice. You might rather just see the screen. Okay, yeah, we got a little picture there. So might need to do something my end. Hold on. Okay, right. Oh no, it says I can't start my video because the host has stopped it. Okay, never mind. Yeah, I mean, I think that does have a role. I guess you go back 30, 40 years, and there were quite a lot of overnight trains, even in the UK. There's now only 2. There's sort of London to Cornwall, and then there's London to Scotland. But there used to be ones from sort of, you used to be able to go from sort of Plymouth through Birmingham up to Scotland and that kind of thing. And that all really stopped, partly because trains got quicker. So most of those journeys could be done during the day. But I think the idea of certainly within and across Europe, being able to travel perhaps overnight by train is definitely something which has got a role to play. The real problem, I think, at the moment is that it can be prohibitively expensive. So I do think that there's actually got to be a strategy about making public transport affordable. Public transport is kind of quite good. Traveling by train is okay if there's one of you or two of you, but you start to have a family and it starts to get very, very expensive, as well as the logistics get difficult. So I think the short answer to your question is that I do think that better coordinated, more accessible, and better priced overland transport over longer distances has definitely got a role to play. Okay.
Hi, yeah, that was really interesting, thanks. I thought it was really interesting that you mentioned the Great Western Electrification Project, because I actually worked on that partly before I came back to academia, and was part of Midland Mainline electrification when it got cancelled. And talking about a 10% shift, doubling the rail capacity, the scale of investment required for that is, 7 or 8 HS2s, which we all saw how that ended. How do you think we generate the political appetite for that level of investment in rail infrastructure, especially in the north? Because every project that got cancelled was usually in the north. Midland Mainline electrification, for instance, they decided to electrify it to Bedford instead of all the way to Sheffield.
Yes, I mean, it's the trouble is, I think the industry we shot ourselves in the foot on Great Western, and a colleague and I were called in when somebody at Network Rail realised that the foundations for the overhead line equipment were sort of 3 times what they'd expected. And I do remember that we had a discussion with one of the consultants, and I said, look, this is not about. It turned out that they had actually done very, very conservative calculations, and I think they'd really sort of lost the confidence. So I think that initiatives such as the RIA, the Rail Industries Association, they've had a real push on trying to demonstrate it doesn't need to cost this much, we can do it more affordably. And I think that was partly responsible for getting the Midland Mainline electrification restarted. I think that actually not having to size everything for peaks and spreading demand is actually quite an important part of it. And the same is true with roads. It's been quite disappointing to see a lot of road schemes go ahead because they're actually addressing problems that were pre-pandemic in the sense that the road gets clogged up for a couple of hours in the morning, a couple of hours in the evening. And I think you've got to provide people with alternatives. So I think in terms of how do we persuade government, I think some of it is about demonstrating that the industry can do it. I think it's that the industry can do it sensibly, economically, and at a reasonable cost. I think some of it is about demonstrating that we have got the ability to make people want to use the new facilities. I mean, the interesting, HS2, I felt we never really got that argument across, and it was about capacity. HS2 has actually got enough capacity to empty one of the London to Birmingham motorways. It is ferociously efficient as a conveyor of passengers from one place to another. And I think probably the most convincing thing we can do is actually, when we're given opportunities to restart things, demonstrate that we can really make it happen, not at a stupid cost, and we can make it happen on time. I think actually it is down to us as an engineering industry to deliver these engineering solutions, which is what you're all on your CDTs for, which is great.
Hi, Alan Dunbar here. You talked about there being 10% of transport going via rail networks in the UK. Do you have any idea on how that pans out in other countries? And are there examples elsewhere that we can learn from, where perhaps they're doing these things slightly better than in the UK because of a difference in infrastructure?
Yeah, I mean, I think there is an interesting question about capacity, because there's no doubt that some bits of our network are full. And I think that probably evening out demand over both time and geographically is important. I think levelling up is not necessarily just about north-south. I mean, I think there was an interesting statistic that a female born in Southampton had 12 years less life expectancy than a female born in north of Hampshire. So, you know, actually just within that same county of Hampshire, you've got these huge inequalities. So I think some of it is you know, the levelling up agenda is important. I think some of it is about using spare capacity, because the reality is that we've got no capacity at some places, we've got capacity at other places. If you go to the Netherlands or Germany, a 5-minute connection is expected to work, and it will usually be organised, so it's the same or across the platform. We've kind of got to the stage that we don't trust connections at all. So that actually puts a lot of people off from making a journey if there's no through train. I think there are also initiatives so that train fares are, I think, more affordable in other places. I think it's probably a sort of a more predictable, a more useful service, and they make better use of connections. They maybe sort of run the thing more as a bit of a network. China is interesting because when you look at their high-speed rail network, it is utterly awesome. So I've traveled on that, and I think I went from Zhejiang to Beijing, and you know, the station in Zhejiang, it wasn't really recognizable as a railway. It was more like it was massive, you know, sort of 18, 20 platforms with these high-speed train departures. It's also interesting that what China have done is they've connected up all of their major cities with a population of more than about 5 million with high-speed trains. And you know, in some sense, in the UK, we're very London-centric. We're not a huge country, so we don't really have that. So I think that there are some lessons that we can take from other administrations, but we do need to be aware that there are geographical and political difficulties. The other one, which I think is definitely worth looking at, is what can we do with freight? Because pre-pandemic, it was, oh, there's no room on the network for freight because it's just full of passengers. Actually, maybe we start to think we should make room on the network, or there is room on the network for freight. And we need to think about, from a national transport strategy point of view, not road v rail, you know, where is the freight best placed? I think there are challenges, because there's no doubt that heavy freight knocks hell out of your infrastructure, whether it's a road or a railway line. So it would need quite a lot of careful thought. But I think that is an opportunity. And of course, in America, for a long time, their railroad has been primarily a freight railroad. I'm not saying that I would want to go there, but I think we need to look at how we can solve capacity issues without having an enormous cost. So I think we can learn things from other countries, but we've got to be aware that there are sometimes different political things we can change. Geographical things and sort of population distribution and density are much more difficult to change over a short period of time. But there are undoubtedly lessons we can learn, but we need to be quite selective about taking the ones that are relevant.
Morning on again. Can I just ask, do you think one of the solutions is potentially renationalising the rail or bus system?
So,
as you see, a provocation.
Yes, it is a provocation. I mean, as some of you will be aware, that we're about to move into the realm of Great British Railways, and it's a sort of interesting thing that, you know, actually, if something's a bit crap, you can make it good by putting the words "Great" and "British" in front of it. I started my career as a railway civil engineering trainee with the old British Rail, and when you look at what British Rail did in terms of, it not only owned and ran and maintained, it built the infrastructure. It pretty much, you know, nearly everything was in-house. It was very rare for an external firm of consultants like Mott MacDonald or whoever to get involved in railway civil engineering. It did all the signalling, built all its trains, it ran the trains, it operated the tickets. I just, you know, I don't think even Great British Railways is going to get back to that. And it's very difficult to see how it could. And I don't quite know why that is, because it used to be possible, but it maybe is just like you gradually get to the stage, you know, you do more and more and more. And then when you stop doing, to go back to where you were is quite difficult. I suspect there's an element of that with GBR. I think there certainly needs to be, it's got to be done in a holistic way. And I think certainly you need to be looking at integrating different forms of transport. And if you dogmatically chop it all up so that buses compete with trains rather than feed into trains, then you start to lose the benefits of doing that. Does it need to be nationalised? If it is, I think it would be better as an arm's length body, in a sense like British Rail was. I think we have seen DFT guidance of procurement of new trains and franchising and so on. And I wouldn't say that that's necessarily gone terribly well. So I think you have got to have a responsibility and accountability with whoever it is you charge to do it. So, yeah, we'll see what happens with Great British Railways. But certainly I think there is a hope that we get back to the idea of a directing line. And I also hope that within the DFT, they would start to see that we do need a national integrated transport strategy, so that we actually get different modes to do the things which they're good at rather than just think they can all compete. So I haven't answered the question. I mean, the answer is it could be, but it might not be, because I think it's a little bit like most sort of management structures. It's not necessarily the structure, it's the people and how it operates that make the difference.
William again. Which is Harriet.
Okay, thanks everyone.
And the title of the talk will be qualitative comparison.
Does it come up on this screen as well? Okay. Sorry, hi. Right. And which buttons?
It's just the
Okay. Right. Hi everyone. Yes, that's the title. It's rather a long title, I'm afraid. I wanted to get everything it was about in. Anyway, I'm Harriet. My supervisors are Zunli and Olgan, and I'm talking about liquid gas and solid gas thermochemical storage systems for inter-seasonal storage for heating and hot water. This is nothing about electricity, okay? Yeah. I'm going to give you a little introduction to the area, and then I'm going to talk about design considerations that are consistent between the two different types of liquid gas and the solid gas. And then I'm going to talk a little bit about the liquid gas and then the solid gas, come to some conclusions, and that's the end of the talk. Okay, so firstly, there's an unmet need for low carbon heating and hot water. And one way you could solve this, we've got a pointer on here. Yeah, is to use a solar thermal collector connected to some form of interseasonal storage. And of the types of interseasonal storage, thermochemical is the most suitable of these for a number of reasons, which I will discuss on the next slide. Firstly, what is thermochemical storage? Well, it's a reversible chemical reaction. It's room temperature storage, where the charging of the store is an endothermic reaction, the discharging is an exothermic reaction. You can classify them as, oh, my slide has gone wrong. The E should be up there, and E should be up there, E should be up there. Anyway, you get the idea. So you've got the you charge, you provide heat, you separate off the sorbate and you separate them, leaving the thing you store at room temperature, and then you combine them again on discharge, releasing the heat. Then you've got the closed system where both are stored. And that's normally if you've got one of the components, there might be a toxic element to one of the components. And I will be looking at liquid gas and solid gas. And for a liquid gas system, you use a dilute solution and you basically make it more concentrated and you drive off the gas. For the solid gas, you take a solid, you add the heat, and you end up with a solid with less of the extra component in it. And for my study, I'm going to qualitatively look at liquid gas, and I'm going to look at open, low temperature with the sorbate being water. Okay, now let's see if the next slide will work a bit better, because this one's, well, this one's not too complicated, but this is basically just illustrating the common things where you've got a solar thermal collector. For all of them, I've put a hot water tank in and a thermochemical store. For all of them, I'm going to have heat recovery from the water on charging. And for all of them, you're going to be able to directly charge the hot water tank from the STC, bypassing the store. You're going to be able to do direct charging of the store from the solar thermal collector. You can then discharge either straight from the hot water tank, which is at a higher temperature than you need for the heating circuit, or you can discharge just for hot water, or discharge for heating alone, or for both. And an optional putting a heat pump in there for when your store is depleted. So that's the common design considerations. Now let's move on to liquid gas absorption. Right, there's for this, I've considered a combined tank here, which is separated by looking at a differing density between the concentrated solution and the dilute solution. So as you charge, you take the dilute solution into your reactor. So there's a separate reactor. You heat it by the solar thermal collector, and you make the concentrated solution, which is then pumped back into the bottom of the store. The water is then evaporated, and that goes into your hot water tank, leading to some heat recovery. On discharge, you will take the concentrated solution, you add the water back in, both from the mains and from a little bit from the hot water tank to get the water temperature right in here. And then that releases the heat for the heating. Okay. There are a number of active materials you can use for this. You could use lithium chloride or lithium bromide, but they are both expensive. You can use calcium chloride. That's unfortunately got a lower energy storage density. You could use potassium hydroxide or sodium hydroxide. Both of these are highly corrosive. And of the ones that you could use, I think potassium formate is the less corrosive, and it's cheaper than lithium chloride, so that's probably your best option. You can also add in an option of controlling the air pressure in and out of the reactor, because that helps you control the temperature uplift for the heating and the hot water circuit, and the option of a hot water tank. So that's system A, okay? And we're going to now compare it to system B, the solid one. Hey, it's a lot more complicated, and that's because it is so hard to move a solid. Yeah, it becomes, so you then have to consider, and in this case I've considered a modular design, because it's difficult to move a solid. So I've considered a modular design when I've illustrated here the charging through module 1 and the discharging through module 2. And these are in my diagram, I had little blue spots in there to show the material, but it's not come out properly on this. But so this is where your active material is, and you have to pass air through it and provide heat as well, and that then evaporates the water off, which is then condensed back into hot water. On the discharging circuit, you add the water, and the air then leads to moist air being brought into your active module, where it then provides your heating and the hot water. So there's 3 different types of solid gas sorbate. The first one is absorption only, which is like a zeolite, but that's a low active material storage density, and that's expensive. Second type is one's based on reversible salt hydrate, so taking the water in and out of the salt hydrate, but there's some material challenges with those. And then there's composites, which is a mixture of the two really, where you put an active material like salt hydrate onto something like some sort of substrate, so that you get over problems like it melting, that sort of thing. Of the individual salt hydrates, the best in terms of good stability and cycling and that sort of thing, and having the right temperature for the reaction, is probably potassium carbonate, but this is a low active material storage density. And if you actually consider how much more complicated this is compared with the other one, the actual material storage density, by the time you've got all the gubbins in that you need as well, takes it back to about the same storage density as you get with the liquid systems. Okay, so if we then have a look at what my conclusions are, I've only considered open storage systems with water as a sorbate and heat recovery via direct condensation of the water in the hot water tank. That's, for the liquid gas, the combined tank based on density difference improves the system storage density, obviously, because you don't need two separate tanks, one big tank for the dilute solution and one smaller one for the concentrated. Possibly this is therefore the quickest route to commercialization, because you have not so much trouble with pumping and moving the liquid. Best liquid gas couple is probably potassium formate, and the next stage of looking at this would be to do a quantitative analysis to actually look at the numbers and see how feasible this is, and look at the thermodynamics of the reactions. For the solid gas, you can see that there's a clear disadvantage of using a modular system. It's a lot more complicated. It takes up a lot more room in the store. I forgot to mention as well that the store has to be insulated. If the whole of the store has to be insulated for the modular device, but for the liquid store, it doesn't, because you've got a separate reactor. You need to, if you could find a method of moving the solid without damaging it, without turning it into a powder, so you could still pass, so it still keep its structure and everything like that, and you could still pass the air through it, and with reasonable kinetics and things like that, you could then maybe start to consider a solid gas system. And then I would say that something like potassium carbonate would be a viable option. But a lot more research is needed on this area, certainly even just at the materials level. And so this is hence really much less commercially viable in a shorter time frame than the liquid system. So that's my conclusions. And I'd like to acknowledge the Facility of Engineering and Physical Scientists at the University of Southampton for funding me. And of course, the CDT here and energy storage. Right, thank you. Any questions?
So you mentioned all the disadvantages with the solid gas systems. And if the research were to be put in to overcome those disadvantages, are there any then advantages of that system compared to the liquid gas system? Why should we push that forward?
The liquid one has a the liquids tend to have a lower regeneration temperature, but that also means they have a lower uplift temperature. So they become a lot harder to actually work for hot water generation, which is the one that needs the highest temperature. And they are lowest active material storage density than the solids are. Some of the solids have much higher active storage densities. But that's active material storage density. That isn't the whole system, if you like. Yeah. And so the advantages of the solids is that you've got a lot more choice as well, and they're not necessarily as corrosive and that sort of stuff as some of the liquids. Yeah. And you get a better temperature uplift. So you might not have to have big lots of underfloor heating in your house. You might be able to do it more with radiators at a higher temperature, for example. So there are further on in the future advantages of using a solid system, yeah, but they would be difficult to overcome a lot of the disadvantages of having to try and work out how the hell you move a solid about without it becoming a powder very, very quickly, and then you can't get any air and moisture through it. And the other thing, the solid you get, obviously, as you add the moisture, it tends to swell. So you have to leave room around it to allow it to swell, to actually allow it to take up the moisture and release the moisture. So, yeah, liquid systems, I think.
Is it a fair, sorry, is it a fair comparison in terms of application? So is this the application that you would use solid storage for, or would you use it for more of a centralized kind of heat network system where you could control some of those things? And what was, if you're making the comparison between the liquid and the gas liquid and the solid, what's the difference in volume that system would take up for a particular house, for example? If you're deploying this kind of system, how big would the storage system have to be to meet the demand?
Yeah, I looked at how large, or roughly how large, storage would have to be to meet the demand. And if it's a once only charge, it's actually still quite a large store, but it's a lot smaller than a sensible, hot water storage system, which isn't suitable for interseasonal because it sort of loses its temperature with time, whereas this is room temperature storage. It's about 4 meter squared, 4 meter size of a room, roughly. Yeah, is roughly about the sort of size you're talking about. The smaller side, if it's a once only charge, but if you could do more than once charge a year, if you like, so you could, partly charge it and partly discharge it as you need it a bit more, it would become more feasible for smaller. So yeah, it's the only type of thermal storage that isn't massive to meet the requirements for one house, because the requirement for one house is about 12,000 kilowatt hours in terms of heating and hot water. And that's a median, I think, from about 2016, if I'm right. Yeah. So it's a big energy requirement. You couldn't do it with a battery. Yeah. Or you could, but it costs you a lot.
All right, can I ask you if you had a choice to either put PVs on your roof and use that as a solar capture, therefore take the electricity, or do a solar heat, which would be more cost effective?
I would actually, I know my PhD is on the thermal one. PVs are a lot less hassle. You don't need water being pumped up or a liquid being pumped, because in this country it'll be water plus ethylene. You don't need the complex circuit. You don't need necessarily a hot water tank in your house, although I would advocate having a hot water tank because it's storage. And PVs tend to be quite, but they're not as efficient. PVs are lower efficiency per area route. So, you know, for your hot water tank, three square meters of solar thermal will give you enough for all your summer hot water. Yeah. And then you could have PV as well. Yeah. But PV, solar thermal isn't actively encouraged in this country. It really, there's not much yet for putting a solar thermal system in. And if you have to put a hot water tank in your house as well, that adds to the cost of the system. The cheap and cheerful that you see in Greece and sort of where they've got when it's the tank is above the collector and it's all gravity fed and everything, those really work very well in hot countries and they're cheap. Yeah, and they're a good solution for other countries.
Thanks very much. Yeah, that was a very interesting talk. So my question is, yeah, the aim of the game is always to convert some other form of energy into potential energy, either chemical or something else. So my question is there an inherent advantage to doing this at a local level, you know, a per house basis, rather than just building a giant reservoir up a hill and pumping the water up the hill and then releasing it when you need it?
Yes. Well, the inherent advantage is that the heat that you are releasing is where you want it. So you don't have all the losses from the piping from a main central thing. So, you know, a main central sort of system works if you are a high density of houses that are then taken from that, but you get quite a lot of losses if it's out in the British countryside somewhere. So there are some advantages of thinking on a very local generation, local use system, but you could have loads of solar thermal collectors in fields and then make the dry stuff and then transport the dry stuff on your roads using fossil fuels to get them to other places. So then, you know, then you could people would buy it like they used to buy coal. That's another way of doing it. Yeah.
Yeah, thank you very much.
Good morning, and thank you for inviting me to speak at the conference. My name is Tracy Levi, and I'm a PhD researcher at the University of Southampton. I'm conducting research which is funded by the EPSRC and sponsored by Network Rail. My supervisors are as indicated on the screen. Today I'm going to be talking to you about carbon footprinting of railway embankments and cuttings. I'm specifically going to be talking about a framework for reducing the embodied carbon and investigating the offsetting to reach net zero carbon via a movement away from linear projects towards more circular projects. Here's an outline of what I'll be discussing this morning. I'll begin with an introduction, a discussion on life cycle analysis, the methodology and the proposed framework for the research. Then I'll briefly discuss results and conclusions. First of all, why do we need to conduct this research? Why are we interested in carbon? Well, it's unequivocal now from the latest IPCC report that temperatures are rising and that action needs to be taken. Warming needs to be limited to 1.5 degrees C above pre-industrial levels. Now, the government has acted on this and has set targets, beginning with the 2008 Climate Change Act. They then went further in 2019 in the amendment to the Climate Change Act, whereby all carbon emissions must be close to zero by 2050. Network Rail, in line with this, has set up its own environmental sustainability strategy in 2021, again committing itself to net zero carbon by 2050 in its operations. Now, the scale of the carbon problem is known. The below figures from BICE on 2021 show that the total UK carbon emissions were 454.8 million tonnes of CO2e, which is carbon dioxide equivalent, which includes all of the Kyoto baskets of gases. Transport accounted for some 27% and rail for some 0.4%, which is still a large figure, albeit in itself, 1.7 million tonnes of CO2e. Now, this study is concerned with railway earthworks, which, as you can see, lay here within the earthworks in the railway infrastructure chart. Within earthworks, there are 4 areas. 3 of them are of concern to this research. They are embankments, soil cuttings, and rock cuttings. This chart has been taken and amended from the Network Rail Costs and Volumes Handbook. I'll now zoom in a bit on the areas of concern for this research. So, as previously mentioned, embankments, soil cuttings, and rock cuttings will be looked at over 3 different lifetime interventions for each, which are maintenance, refurbishment, and renewal at 2 years, 20 years, and 120 years respectively. For these different lifespan interventions for each intervention type, case study analysis will be performed looking at materials, material transport, plant and machinery transport, transport of staff to site, and waste removal, all in alignment with PAS 2080, stages A1 to A5. Now, you're probably asking yourself, what are geotechnical solutions? What are embankments and cuttings? Here's an illustration of an embankment where we build up the earth to get a nice level gradient for the train, and cuttings, which can be rock or soil, where we dig down again to make a nice smooth gradient for the trains to pass and the tracks to lie on. Now, Network Rail has set itself ambitious science-based targets for carbon reduction, which fall in line with its control periods. As you can see, working off the baseline, these get more ambitious year on year. The first target to be reached will be in 2024, when a 25% reduction on the baseline is required. This is all so that they can stay in line with this reduction to get to net zero by the final control period shown here. Now, this research is concerned with life cycle analysis and carbon accounting of sites. Now, the aim is to have 9 sites per region, of which there are 5 regions in Network Rail, and ideally 3 examples of each, giving 27 per region. Now, first of all, a suite of sites need to be identified, and these are for each intervention type: embankment, rock cutting, and soil cutting. Maintenance, refurbishment, and renewal projects need to be identified from the Cost and Volumes Handbook for that control period, and then data collection and analysis can begin. Now, once the data is received, it then can be analysed against the PAS 28 template, which resides in the Rail Carbon tool created by the RSSB. Now, the PAS 2080 is the infrastructure assessment of life cycle carbon, and it covers these 4 stages: A, B, C, and D. A is the before use, B is the use stage, C is end of life, and D is supplementary or outside of the life cycle carbon. That's where that resides. Here's an example of the carbon data capture form. A blank example is shown here, and this aligns with data for the A stages, which is what is the proposed business as usual case, which is A1 through to A5. So I'm asking here for information about the materials, how they're transported to site, the method of transport, as these will all affect the emissions factors, along with plant and machinery required, again, how it's transported to site, how many hours it's running for, which will determine its fuel usage, and again, its carbon footprint. Transport of staff to site, how many staff came, how far did they travel, did they use public transport, did they drive a car, did they drive a van, etc., etc. And then waste removal, what waste was produced, where did it go, and how did it get there. This data can then all be processed, ready to be input into the RSSB Rail Carbon tool. Here's just a screenshot of the home screen of the Rail Carbon tool for those of you who may not be familiar with it. There are various carbon factors that can be pulled from here. There are templates. There's an area where projects lie. There's a sandbox where you can do your own analysis and calculations. So the carbon data captured from the project form, as I've just shown you, will be analysed, choices made as to which emissions factors to choose, and then it will be input into this tool to calculate the carbon footprint for each project. As you can see here, there are many different sub-stages within each life cycle stage for data to be input. For example, there's items procured as prefabricated building elements, items procured as manufactured construction products. There's also a proportional embodied carbon for construction plant and equipment manufacture in this tool. So there's great scope to really put in every single bit of data so that no carbon is lost or not accounted for. Now, the methodology, as I've mentioned before, and as you can see here, this is a table here which includes the top headings from the PAS 28 chart shown previously. Currently, the RSSB rail carbon tool is little used and only tends to be used for really big projects over $1 million, because that's what the mandate is, that has to use the tool. Otherwise, people don't have to use it, and therefore it is not being used. So the current status is business as usual projects that are in the tool only cover A1 to A3, which is basically just the embodied carbon in the materials. People will say, I'm using some cement in this material and some steel, and they'll put that in. It's not really used much beyond that. My proposal is a proposed business as usual, which will cover A1 through to A5, which is all the data that I'm collecting from sites. This will then be expanded in the next iteration of the footprints to include for the whole life cycle, or cradle to grave, which will include use stage carbon and end of life. This will be, for example, various multipliers of other factors to go in at the different stages. And obviously, it's end of life. The materials that were all brought there will have to be removed, and there will be a carbon cost to doing that. In the comprehensive scenario, A0, the before use phase, will be looked at. This is a phase of particular interest, as this is all the pre-site works. For instance, the survey works, be it desk survey, ecological survey, construction survey, borehole survey, groundwork survey. All this carbon here is currently not being counted and factored in. So this is something that's of great interest to me, to ensure that it's factored in, especially as this is something that particularly is of relevance to renewal works, the 120-year lifespan works. So this is something that needs to be counted towards their carbon. And the beyond the life cycle is any sequestration activities, which could be, for example, tree planting or mineralization, enhanced weather environment mineralization. Now, my methodology here, as you can see, is a very circular methodology. So it's taking this linear approach and expanding it, and then making it into a final circle, whereby demolition and recycling and reuse will feed back in, as in a true circular economy. Obviously, we're a long way from that at this moment in time, but this is just the very beginnings to see how this could potentially work and fit in with the way Network Rail operates at the moment. Now, this circle, as you progress from the inside to the outside, has maintenance, refurbishment and renewal with 2, 20 and 100-year lifespans. As you go around the circle clockwise, you can see you move through the A stages, the B and the C, which then feed back in again to the A, B and C of the next cycle. The D stages, which by their very nature live outside of the cycle, are shown outside of the circle in the dotted square. These are where the sequestration activities and any other carbon offsetting activities would lie. Now, I've put a 120-year boundary around where the D life cycle sits to align with the 120 years of a renewal. However, there is a further factor here which needs to be factored in, which is carbon dioxide equivalents are all measured against a global warming potential of 100 to allow for all the different gases being amalgamated and assessed, as they have differing lifespans in the atmosphere. Therefore, I've proposed a 100-year circle here and dotted outside the life cycle D stages to allow for this, and I'll be making adjustments in my footprints to allow for this, to allow for true comparisons to take into account this global warming potential of 100 when you're dealing with CO2e. Now, moving on to some of the data that comes out of the tool from the data collected. I'm aware that you won't be able to read all of this, it's very small, so I've just put at the bottom here. For example, cement, the actual type of cement will need to be known. In this case, Chem 2 A to L Portland limestone with 13% limestone. Then the actual where the methodology behind the emission factor is going to be will be detailed. For example, this comes from the Bath ICE version 3 and it covers the Europe region. The carbon emission factor value is put in there. And then the single total and project totals of CO2 are indicated. And this is just an expansion of the A1 to A3, where you can see how the life cycle stages are being built up in this spreadsheet, which is a download from the Rail Carbon tool, which is then amended to line up and to be easy to read. This is an example of a business as usual, which is an A1 to A5, for a 120-year renewal of a soil cutting. As you can see, by plotting the graph in this way, we can see where the carbon hotspots are, which is the areas which we would be best to tackle early and fast to get the biggest reductions in carbon, which are needed to meet the science-based targets that were alluded to earlier in the presentation. Now, for this 120-year renewal that's been analysed thus far, potential savings have been identified. These could be made via a movement to electric vehicles for staff transport and material transportation, a change to a lower carbon cement mix, a movement away from fossil fuel powered site machinery. These would all give beneficial carbon savings. Now, in terms of offsetting, I'm going to be researching this further during the course of this research, and it is envisaged that solutions to offsetting will lie in the life cycle stages D, hence the fourth and final comprehensive scenario. And reuse and recycling in terms of circularity lies between C and D in a way, because the circularity is how we're going to bring these items back into use again via my circular diagram, but also other ways outside of the life cycle that things can be reused. So we're taking them out of this life cycle of the railways, but maybe they go into a second life cycle elsewhere. So that's something that needs to be investigated, because then they'll become part of the circular economy for another product. So in conclusion, analysis of whole life cycles via this PAS 2080 approach will encourage Network Rail to move from the current linear approach to a more circular approach, and hopefully towards using more circular economy principles in their projects. Thank you very much for your time. If you have any questions, if you could please direct them to me via email, I'd be more than happy to answer those. Thank you again. Goodbye.
Good morning, everyone. Everyone's had a nice coffee. My name is Ben Craig. I'll be taking over the chairing now for the second half of the first session. Hope everyone's enjoying the talk so far. The next talk is by Andrew Hutchinson, and it's verification and analysis of a battery energy storage system model.
Thank you very much. Okay. Hutchinson, and I'm going to be talking to you today about verification analysis of the battery energy storage system model. So a bit of an outline of the presentation and what we're going through. So first I'll introduce a bit of the background of where we got this model from. Then I'll talk a little bit about the actual model that we developed, and then how we verified that model, and then discuss a couple of conclusions. So this model is based on the Willenhall energy storage system, which is a 2 megawatt energy storage demonstrator facility located just outside Birmingham, that's owned and operated by the University of Sheffield. It was, when it was constructed, the largest of its type in the UK, and we use it for a variety of both experimental and functional purposes. So we can basically ask it to do whatever we want. It does do some commercial services for National Grid, but it also presents an opportunity for us to be able to ask it to do any different kind of application that we'd like and judge its response. So the objective of this work was to create a Matlab and Simulink model that accurately reflects the real-life performance of the Willenhall energy storage system. And we did this by using root mean square error, which is a way of testing how close two sets of data are together, to determine the accuracy of the simulation compared to real-life battery management system recordings taken from Willenhall. And that's Willenhall BMS, so that's the inbuilt Toshiba battery management system giving a state of charge reading, and the Willenhall Dspkf, which was an algorithm developed by our research group that more accurately monitors what the state of charge is at any given moment. So this is the main expert of the model. In Matlab Simulink, we use a integrator as a bucket model of the energy storage system. So that means we're just filling up and draining what is effectively a bucket for each second. Whether you're charging, you're adding to it, and discharging, you subtract from it. And then we've also got a lot of different elements to this. So degradation, we've got self-discharge rate and efficiencies, counting the cycles, what the maximum available power is at any 1 second. And then also all of that comes through from the initial starting characteristics that we have there. So this is the main crux of the model. It's quite a basic but very accurate way of modeling energy storage. So we built this out of modular components. So the whole model together can be rearranged to suit whatever applications we need. So the four main blocks is first of all the application block. So that basically tells us what we want our battery to do. In this scenario, that little excerpt there is for providing dynamic frequency response for National Grid. So it's just converting a clock into frequency data that we've taken from the internet, and then converting that into a response characteristic, which we then ask the battery to deliver. That then goes to the control block. So the control block has three inputs. It's what the current state of charge is, what the available power from the battery is, and what the request is for that second. That's just a Matlab function that then determines, based upon the inputs, whether the battery should charge or discharge, or whether it can't do either because it's hit a state of charge limit. That then goes in a closed loop into the battery block. So it asks the battery to either charge or discharge. You add or subtract from the integrator, and then that feeds back ground for the next second of operation, where you're then assessing the new state of charge, the new available power with the new request. And then finally, we've got the metrics block. That can be outputting anything that we wanted to, really, you know, number of cycles, amount of years before replacement, income over a period of time. And what we generally do is we program this into Matlab to then spit out at the end a Excel spreadsheet, which we can then use for further analysis. So to verify this, we did two verification types. The first one is the top set. So that was the step change profiles that we did. So we took these power profiles that the Willenhall energy storage system had performed, and we put them into our model. And we tried to get a good variety of different types of step change profiles. So, you know, like the small increasing steps, the longer drawn out charge discharge cycles, and monitored the state of charge both from Willenhall and from our model. And then we also did, for frequency response services, we did the same thing. So we picked another 6 power profiles, all of about 2 hours in duration, to then manage the state of charge from those ones as well. Before I go into the verification of it, I'll just talk a little bit about how we made it as accurate as possible. So this is just one example of how we refined the model, just to give you a flavour of how we did it. And what you can see here is the first instance of running one of those profiles, and the blue line is the Dspkf algorithm's state of charge. So that's what one of the readings from the battery, and the orange line is our model state of charge. So you can see from that first step that whilst it's very close on these downward and upward spikes, it gets further and further away as the simulation runs on. So that actually had an RMSE value of 2.819%, which is still not terrible, but we obviously want it to be a lot closer than that. So what we did was we changed the charging efficiency, the discharging efficiency, and the self-discharge modifier to incrementally improve that RMSE value and get it closer and closer. So as we changed it, you can see going to B, C, and finally D, that's simulation 10, we actually ended up with an RMSE of 0.422%. So that's a lot more accurate. And so what we were trying to do with that is we don't have, you know, set values of charging efficiency, discharging efficiency, self-discharge from the Willenhall battery. It's been operating for years now. So those characteristics have changed. What we were trying to do was actually figure out empirically how that performs now. So that's probably the best estimation that we could have got from that. So the step change validation, here you can see remember we had 6 different profiles for the step changes. This is showing for verification set 1. And you can see on the left comparing with Dspkf and on the right with the BMS. And when we measured the RMSE between the 2 installed BMSs at Willenhall, so the Dspkf and the BMS, the difference between the 2 was actually 1.41%. So that's how much they disagreed with each other. When we did the BMS in our model and the Dspkf in our model, that ended up 0.96% and 0.94%. So we were actually getting closer to each individual type of battery management than they were with each other, which is definitely promising information. And then you can see here how closely this is aligned. You know, the lines are basically blurring together at this point. So that's really, really happy with that. This one kind of illustrates why the BMS is considered to be a less accurate version than the Dspkf algorithm. Because you can see here these little steps, and that's because the granularity of the BMS system isn't as strong as the Dspkf. So it only goes in increments of 0.1. So when this one, you might have 90.19846. You'll just have 90.2 on that. So it is a little bit harder to get accurate according to the BMS and when compared to the very high resolution that both our model and the Dspkf algorithm have. Then frequency response validation. So again, same thing. This is for verification 7. And you can see with this one, it was a little bit harder to get really close to the lines. And that's because on this one, we're charging and discharging constantly. It's not a smooth, 1 megawatt for 10 minutes and then off. It's all over the place all the time. But you can see again that we are actually very close on the Dspkf algorithm. There's only minimal aspects where that peak is just a bit off, or that discharge is just a bit off. But then with the BMS, there are actually quite a few significant differences. I say significant, they're still only about 1 to 2%, which is still fine, but it's harder to mimic this than it is the step change profiles. With this one, the disagreement between the two installed elements at Willenhall was 1.26% on average, whereas between the model and the BMS, it was actually 1.61%. So we were finding it much harder to model this than the step change profiles. But when we compared it with the Dspkf algorithm, which is considered to be the more accurate algorithm, we actually got an average difference of 1.16%. So that's really, really encouraging results again that suggest that hopefully I answer when we're simulating this. And you can see as well that it varied quite a lot depending on what period of time we were taking and which system we were measuring against. So the furthest away we got was 2.78% average RMSE, but the closest we got was 0.25%, and 0.25% is really small. We were essentially getting exactly the same results for that one. So to summarise on this, I have sped through it as I thought I would. This is 4 minutes shorter than it was when I practiced it. We introduced a model with modular Matlab and Simulink components so that it can be easily modifiable to different applications and different metrics as well. We've refined that process, that model through a process of gradual incremental changes to make it as accurate as possible when compared to the real world installation. And then we measured how accurate we've made it in the end with a recorded overall average RMSE of 1.29% compared to the BMS system and 1.05% compared to the Dspkf system. So on average, about 1.15% out from what the recorded value is at the real world installation, which is definitely within the realms of accuracy that we want. And it ranged between 0.25% and 2.78% in general. So certainly within 3% error is something that we're very happy with, but obviously scope for improvement as we continue the incremental development of the model. Thank you very much. Any questions?
Andrew, for that talk. That was really interesting. And since you finished 4 minutes early, I'm going to take advantage of that and ask a question of my own before I go to the audience. Okay. This question is contingent upon me remembering something accurately from the first year of the CDT. If I do, I'm leaning over like this, I could just stand up, couldn't I? Am I correct in thinking this is a lithium titanate installation?
Correct, yeah.
And how well does your model translate to lithium NMC?
Our model is fairly broad. So in terms of battery chemistries, it's very easy to translate that into a different installation. We did this refinement process to try and mimic Willenhall, but generally it can be took as a fairly generic battery energy system, and you can modify certain components of it to represent the different degradation mechanisms or life cycle of that specific chemistry.
Thanks a lot. Okay, to the audience.
Yeah, thanks, Andy. So you've done the comparison between the state of charge of the model and the system itself. How about the measurements or like the differences between currents and voltages? How about that?
Yeah, so I don't have current and voltage in my model. It's taken on purely a power and energy basis. So we're not modeling the specific way that battery is performing with regards to voltage and current. What I will say is we have performed basically the same analysis on power output. So we've taken the power profiles that you saw previously. So So these, we have put the frequency in rather than the power to measure how we are responding, whether we're responding correctly. And we got fairly similar results, as you would expect, because it has to be operating very quickly if it's going to get the SOC results that we've presented here. So yes, we have also done a power-based verification study on this.
Andy Cruden.
Thanks, Andy. So can I just check the table of changes or that bottom table? So those were the parameters you then fix. So all your following results are based
on Sim10, yeah.
Okay, cool. So let me start with a daft question. Why model it in Matlab if you already had that Dspkf system that you think is quite accurate?
Basically, that's so that we can model different applications with it. So the Dspkf algorithm is installed at Willenhall to generate what the SOC is at every second. But that's only when we ask Willenhall to do certain profiles. So we have to physically program it, agree it with National Grid to get it to operate like that. Whereas this, we can just do anything. Simulations take 10 minutes to simulate a year.
All right, okay, so thanks. And just final point, how long have you run those simulations for? Because those
the verification ones.
Yeah.
Yeah. So we have ran some of them for 2 days of doing the step change profiles, and it didn't really give a significant difference. It doesn't converge away, which is what I assume you were maybe driving at. With the frequency ones, we're limited by how long it can operate as a frequency response service. So we're kind of limited to in the 3 to 4 hour region.
Well, apologies that the maths has come out.
And we'll stop it there.
But is the RMSE a good means to assess the fit of those two models? So it assumes certain things about the statistical behavior of the prediction.
Yeah, it does. It's the best in terms of quickly analysing its suitability compared to the real world, but there are limitations of it, like you say. So we will be performing a longer verification exercise using maybe a couple of different tools, but we are sort of restricted by what I said before. You often need larger data sets to perform more thorough verification studies, and we can't get hold of those data sets.
Thinking as much, so there's wider verification, but the RMSE is, it doesn't tell you that your model predictions from those two models are the same. What you need to make that statement is a Diebold-Mariano test. Which requires a bit more simulation.
That's kind of what I'm driving at. Like at this point, we've just wanted to kind of quickly assess whether we're producing what we want to produce. Is the model behaving how it should do? When we go into the final stages of using this model and stuff, we will be looking to do more thorough and extensive verification, like you say.
Okay, fantastic. Thank you very much, everyone. Thank you again to Andrew. Maybe afterwards, if that's okay. Just try and give the Okay, fantastic. Next up, we have Kieran Ball from Southampton. Perfect. Analysis of advanced composite materials for lightweighting, transport, and upscaling of renewable energy systems.
Can I pinch the microphone? So I'd rather stand a little bit over here. Oh, everyone hear me? Excellent. Okay, yeah, so thank you for the introduction. It's really nice to be here in person, and no problem at all. I'll be using one of these things again. So my presentation, what would I want to do today? So I want to take you through the big picture, the background, the motivations of the project and how that relates to this idea of sustainability, particularly structures, infrastructure and transport. I then want to cover the bristly topic, which is what actually is a composite material? You know, what am I talking about here? And then I do want to get a little bit more technical and have a look at the strength and toughness of composite materials and how we can optimize them for more efficient designs. And if you don't know what I'm talking about yet, don't worry, because I'm hoping we're going to walk through it together. We're going to go from a journey from start to end, and you're going to finish this presentation being experts on composites, hopefully. So the big picture, you've got a hopefully nice figure here, which shows several key things. The first thing I would like to draw your attention to is the growth of the carbon fiber reinforced polymer composite market. So from the year 2020 to 2030, it's set to just over double. And there's multiple drivers for that and multiple reasons why more industries are adopting it, and industries that have already adopted it are expanding their use down to CO2 emissions targets, lightweighting, freedom in design. And there's a statistic that comes up quite often in literature, and that's the high strength to weight ratio of composites when compared to its metallic alloy counterparts. Now I want to draw your attention to this pie chart over here. And the two largest sectors in terms of demand for carbon fiber is wind energy and aerospace. And this is quite significant because the aerospace industry is a big polluter, and the wind energy sector is going to be core to our renewable energy plan going forward. I used to have quite a nice picture of Boris Johnson or windswept there, but not for this presentation, but it's amusing. And then there's a couple more things that I just want to point out that are really quite relevant, especially in terms of this idea of sustainability, and that is the use of carbon fiber in high pressure vessels to store things such as hydrogen and other gases. If you can create bigger wind turbine infrastructure, for example, then you increase the efficiency and you can increase the power output from those systems. And lightweighting vehicles improves the efficiency and reduces the emissions. So I've got a statistic up here that for a 20% weight saving in this aircraft, you have a full fuel efficiency saving of 10 to 12%. And similarly, this is significant in other civil transport, i.e. Trains, you get the same benefits. However, you also get the knock-on effect of reducing things like wear on the tracks because you have lighter transport. So now let's tackle, what is a carbon fiber reinforced polymer composite? Well, firstly, what is a composite? Composite is a material that combines two or more distinct materials to make a functional material with superior properties for a specific application. An example being a carbon fiber reinforced epoxy matrix composite. So don't get scared about all the labeling on this diagram. I'm going to walk you through it. So here we have a schematic of a carbon fiber reinforced polymer composite. The cylindrical parts here that are going into the screen are the carbon fibers, and these are embedded in an epoxy matrix. And what you can, and you see that the fibers are kind of bundled together, and this makes up the ply of the composite, otherwise known as the intra layer. And between these plies, you have a resin-rich region, or an epoxy-rich region in this case, which is called the interlayer. So intra is fibers, inter is in between. Sometimes we include additional constituents, and we include things like spherical thermoplastic toughening particles in this interlayer here. And what this diagram does is it illustrates actually the failure of these things can be extremely complex. There's lots of different ways that they can fail and cracks can propagate. But in this case, I'm actually just going to focus on the interlaminar delamination and the intralaminar delamination. So now I just want to introduce you to this idea of a delamination resistance curve, aptly named an R curve. And what this tells you is the amount of strain energy that it takes to propagate a crack for a given delamination length. And that is shown schematically down on the left here. So you have an initial crack in a plate with a length of A0. So you pull that plate apart, pulling the crack faces apart, and you then propagate the crack, and you record this value of the strain energy, and then you do it again, you do it again, you do it again in a continuous process until you get a plot like you see on the right-hand side here, where you see the normalized strain energy release rate against the crack length. Now, this shows three distinct different behaviors for R curves. A rising R curve, where the toughness, so we can alternatively refer to this as the toughness of the material, rises with delamination length, flat, that it's self-similar with delamination length, or falling, where it reduces with delamination length. And what is the relevance of this? Well, if we're designing transport infrastructure, there is an assumption that that your parts or your structure needs to be able to operate in the presence of damage and cracks, which means you need to account for this minimum value here. So if you have a material where the toughness reduces with crack propagation, then suddenly you're not going to be optimizing your material because you're going to have to over-design it to compensate for this. So really what you would like, best case scenario in design, is a flat or rising R curve. So now what I want to show you is a real R curve. You've seen the schematic ones. Now this is one of my ones. It's a little bit messier, but it's the same principle, right? So you've got the strain energy release rate on the y-axis again, and you've got delamination growth on the x-axis. 6 specimens have been tested and plotted here. A polynomial curve is fit to the data, and then 95% prediction interval is shown by the red band based on that. So this initial value is where the crack first propagates, and this is known as the critical strain energy release rate. As the crack begins to propagate, you see there's a drop in toughness, followed by a very small rise, which is caused by small amounts of fiber bridging. And then you have more or less self-similar crack growth. But the question that's raised from this is, what is causing this drop in toughness? What is forming this R curve behavior? Well, if we look at the crack surfaces here, and you're thinking, well, what's the crack surface? Well, as I said earlier, to propagate this crack, we have to pull a piece of material apart. So we pull it apart until we fully separate it, and then we put our crack surface down on the table, we look down on it, and that's what we see. This first one has been taken under an optical macroscope. So we see the whole fracture surface, and you'll notice 2 distinct regions, the interlaminar fracture region, indicated by the lighter grey, and the intralaminar fracture region indicated by the darker grey. And you'll see this distinct finger-like structure, which is indicative of the fact that the crack has transitioned from the interlayer to the ply. And it seems to be this that is linked to the drop-in toughness of the material. Now, if we look slightly closer using an optical microscope, we can again see the intralaminar region where the fibers are horizontal. And we see the interlaminar region with the slightly rougher topology. And then if we look even closer with an SEM, we get this really nice depth of field, and you can really clearly see where the toughening particles in the matrix have been pulled out and cavitated and create this rough topology, and then this kind of clean crack along the fibers. So there's been some sort of transition that has had a knock-on effect to the toughness of our material. So these destructive imaging techniques are really good at telling us that there's a link. It tells us there's a drop in toughness because there appears to be some sort of transition. But what it isn't as good at telling us is why this happens. And what tells us why this happens is non-destructive imaging techniques. I've got a little list here. This is by no means extensive. I'm actually just going to focus on X-ray computed tomography because that is what I've used in my project. And if you're thinking, what is X-ray computed tomography? I very handily have a little schematic to explain the basic concepts. So we have an X-ray source where X-rays are generated by accelerating electrons at a target, typically tungsten or molybdenum. These electrons are then emitted towards your sample, which is on a rotate stage and rotates 360 degrees. And the X-rays are attenuated according to the density of the material. These are then projected onto a detector, and several images around the 360 degree rotation, and later reconstructed to give a 3D representation of your sample. Now, I think the main strengths of this, apart from being a non-destructive imaging technique, is that it's suitable for both in situ and ex situ imaging. So what I mean by that is you can do your experiment in the scanner, you can scan your specimens before your experiment, after your experiment, and not alter the state of your specimen. And also you have great freedom in what you can actually scan, the sizes and the resolution. So we can go all the way from less than 1 micron to hundreds of microns. So we can look at features in samples that are millimeters to structural members, which are meters. So it can be very versatile. So picking up on this in situ thing, I just want to quickly explain an in situ wedge loading method for these samples. So on the right-hand side, these 3 images, you can see a basic schematic of the methodology. So what we do is we put a wedge into the sample at the top to open up the pre-crack in the sample, and we scan just ahead of it so we can get a visualization of the undamaged composite. This is really important. And then we push the wedge in a little bit more, and that propagates the crack by pushing the arms apart, right? And then we do it, and then we image it, and then we push the wedge in a bit more, and then we scan it again, and then we do that for as many load steps as we want. So now we've got an undamaged scan, and we've also got a time series idea, a time series set of images of how the crack is propagating, and we can link the two. So what do we see here? This is a scan that was taken at a machine at the University of Southampton at 5.2 micron voxel resolution. A voxel is basically a 3D pixel. So in this, you can think about it as pixel size, if you like. And here the fibers are going into the screen. And what you can see is these ply regions. And in between these ply regions, you can see they're separated by the interlayer. So we have the intra-ply and the inter in between. And you can notice features such as gaps in the fiber toes, resin-rich pockets. And what we see actually is if we relate this undamaged image to a fracture surface and to the damage propagation images, is that we actually get one of our transition regions around here, which is a gap in the fiber toe. And then if we look below, what we're now looking at is a slightly different orientation, right? So our crack and our fibers going from the bottom of the image to the top. And this is if we're actually looking down on top of the crack front. So at the bottom of the image here, you see, you kind of see the tip of the crack, and what this kind of softer featured region is where the crack is in the interlayer, and where it's kind of sharper and has a finger-like structure, it's where it's in the fibers. Taking the exact same frame and propagating the crack, we now see that the crack front is towards the top of the image and kind of just going out the top. And what we see is that we've actually had some sort of spread of the crack from the interlayer into the intralayer, so into the fibers. And also what we see is some broken fibers in the wake of the crack, which is further indicative of the crack being in the intralayer of the composite. So we can actually take this idea of microfocus CT a little bit further, and we can go to a place called a synchrotron and do synchrotron radiation computed tomography. This is slightly different in the fact that our X-rays are produced in this very big ring. So we have a LINAC. This is a word I've only ever seen written down. So if I pronounce that wrong, I apologize. But produced by an electron gun and then sent to the booster synchrotron, which is a 300-meter circumference, and there's accelerated energies of up to 6 giga electron volts, and then goes to the storage ring where they travel near the speed of light, and that is 844 meter circumference. Then the X-rays generated by these electrons go off to experimental hutches in the beamlines, and that is really not dissimilar to the schematic that I showed you earlier to explain the basics of X-ray CT. The main differences are we have high energy and monochromatic X-rays. So these are single energy X-rays. And unlike lab-based CT, we have a parallel beam instead of the cone beam, which was in the schematic. And this reduces the artifacts in the image and you get a better quality image. And I think the biggest thing about it is a scan that could take hours in lab-based CT, or even days, can take minutes to synchrotron. So it's got an extremely high throughput. And if we have a look at what these images look like, well, this is the same sample that I showed you earlier, but this is a voxel resolution of, well, is a different sample from the same material system, which is a voxel resolution of 0.65 microns. 650 nanometers. And what you can clearly see here is, again, these distinct layers, which I've pointed out previously, is the ply, the intra layer, and you can actually see the individual fibers in this image. And you can also see the interlayer, the resin-rich region. And what you can actually see in this image is these slightly darker circles, which are the thermoplastic toughening particles. And in load step 1, what you can see is the entire crack is in the interlayer, which is good. That's where we want it. And then when we apply a load and the crack propagates and we scan at the new crack tip, we see that the crack is actually transitioned into the intralayer. And it looks as though there has been a lateral propagation into the intralayer. And also it has bifurcated. So it's actually now both sides of the interlayer in the ply. But the significance of this is we saw that there was a drop in toughness in the R curve. And this can be linked all the way back down to what's going on the micro scale. So this is very much a 3D multi-scale problem. What's going on at the micro scale is having a knock-on effect to what we're seeing on the macro scale, and therefore having a knock-on effect to the efficiency of our designs. So if we loop this all the way back to how we started, the lightweighting of transport and upscaling of renewable energy and how this is relevant, well, I think it's hard to argue that there's going to be a significant role for carbon fiber reinforced polymer composites in this, particularly wind turbines and reducing emissions in transport, particularly in the aviation sector. But we've just seen that to optimize these systems and get the maximum benefit, we need to ensure that the damage resistance and damage tolerance is consistent. But that damage tolerance is extremely sensitive to the crack propagation path that's happening on the micro scale, is then having a knock-on effect all the way up to the test coupon or even structural scale. So therefore, the understanding of this transition of the crack away from the interlayer to the intralayer and the ply is going to be crucial in helping actually optimize the design of our parts. And a more efficient design is going to lead to a more efficient system. So whether that be saving on fuel efficiency or increasing the capacity of our renewable energy structures. But I mean, that's all from me. So I'll be absolutely happy to take any questions, and thank you very much for listening.
Talk. Thank you very much, Kieran. So, any questions? Ruben.
Thank you very much. So two points. I guess first point is a more general point. How recyclable or recoverable is this composite material?
Do you want to ask both your questions and I'll answer, or do you want me to?
I'll ask the second bit. So, and the second one is, based on the work that you've done there in terms of that crack propagation, what could be done or is being done to prevent such cracks in?
Right, okay, I'll start with your first one about the recyclability. There's always an interesting question because it's not the main, well, it's not really part of my research, but it's something, the end of life is something that's obviously extremely important. And I think to be upfront about the fact that actually you're dealing with plastics and the consequences that may have. And I know there's people in here studying microplastics as well who probably just want to give me a slap. Actually, also, but the other thing is that recyclability to them, because after a part has failed or has reached end of service, you don't necessarily have to throw it away. You can burn off the plastic or whatever you need to do to get rid of it, and then you can reuse the fibers. So there is a lot of research at the moment into short fiber composite, which feeds into this idea of recyclability. There's also a lot of research into using natural fibers and other sorts of matrices which can be reused and recycled. I mean, for these are very much high performance composites that we're looking at. So these are like aerospace grade. So I think you are limited to an extent. And I think genuinely that's, that's something that needs to be addressed and is indeed being researched. So the answer is, I guess, to give two words, is sort of. Your second, and your second point, what can be done to prevent this from happening? So the idea of including thermoplastic toughening particles is to encourage the crack to initiate firstly in the interlayer. And the idea is that this interlayer region is then supposed to be tougher than the fiber interface of the composite. Is that actually we see that every time, every single material system we have, the crack fibers. So effectively, what you end up doing is, with a very small amount of crack propagation, you lose the benefits of having that toughened interlayer. And then, further from the experimental work, I've also been doing some modelling work, which I haven't included here. But what we see is these transition regions tend to be related to things like the gap in the fiber toe, like I showed you, and these regions of agglomerations of fast toughening particles. Now, they're not completely even. So there's some really nice research prior, which because it's a competition, right? It's an energy competition. The crack, in a kind of simplistic way, is there, it's ready to propagate, and it's just going to take the lowest energy path. So if you have a toughening particle that's too far away and isn't in kind of the high strain region around the crack, it's actually just going to jump. So that's toughness. So how to overcome this? I mean, it's tricky. I mean, in an ideal world, you want to increase the uniformity of the interlayer structure, and you want to better distribute the toughening particles throughout the composites. And I think that's the biggest thing that this research. Real challenge now is, well, how do you do that? And I guess that will be for somebody else to look at. Indeed, I've given them an interesting problem.
Fantastic. Thank you very much, Kieran. I think that's
Can I ask another question?
Okay.
Thanks. So Siemens in Hull are currently building offshore wind turbine blades. What advice would you give them to facilitate the dramatic increase in those wind farm blade diameters?
Interesting question. Yeah, I think, I mean, the reason we're starting to use carbon fibre in the wind sector, where we haven't before, where we traditionally use glass fibre, is because they're getting bigger. They need to take higher loads, and suddenly the expense for paying for carbon fibre is suddenly worth it. I think that having an understanding and an appreciation for actually what you are seeing on smaller scales certainly shouldn't be discounted. So I mean, there are different ways of looking at this problem and actually looking at, you know, some people look at it from a structural point of view and say what's going on down at the micro scale doesn't really matter. But I just think a good awareness, and also the assumption that your blade with cracks present, with damage, and it needs to have the damage tolerance to deal with that. But I mean, carbon fibre seems like a sensible way to go for wind. I hope that answers your question, sort of.
Okay, fantastic. Let's say thanks again to Kieran. And next we have. Oh, that's the guy. Okay.
I'll set up.
So would you, do we have Hannah to present now? Is she ready? Is she ready?
Hello, apologies for not being there this morning. I have a 3-year-old who has COVID. Luckily, her dad is now on his lunch break. Do you want me, because I submitted my slides, but do you want me to use them off, to put them up on here?
Yeah, please do share your screen.
Just get those.
Welcome, Hannah. Hannah's talk will be challenges and assumptions in modelling energy demand for rural mini-grids, a comparison of survey data and system data from a solar mini-grid in Tanzania.
There we go. I can see, luckily I can see the room, so I can see what you guys can see. So hello, so I'm a PhD student at the University of Sheffield, based in the Department of Geography, but I also do I'm also part of Sol's group because my work also looks at energy. So my supervisors are Dr. Matt Watson and Dr. Ankit Kumar, who are both in geography, but I also work with Sol Brown in engineering. So I'm going to go through a little bit of kind of why did I start? What's the kind of problem of energy access in Tanzania? What did I do on my field work? What did I find out? And what does it all mean? So modelling of energy demand is a key issue for rural electrification. There's a real data gap in terms of the rural communities understanding how people use energy and when they use energy. And so if demand projections are too high, you end up with projects being oversized, and it's difficult to recover those investment costs. If the demand projections are too low, then projects can be undersized, can have reliability issues, as well as limits on the number of customers that can be connected or how people can use electricity. So a common issue is that they're actually oversized. And so people technically might say that they're successful because they're 100% reliable, but when you look at how much that ends up costing households, then you come into other issues. So a big problem identified in the literature is a lack of interdisciplinary research. So the reasons that mini grids particularly, so this is community scale energy projects, are unsuccessful is mostly social reasons, but a lot of the published research focuses on technology and economics. And there's also this real shortage of published data on demand, especially because the private sector are quite active in this space and they are particularly reluctant to share their data. So this paper, or this presentation, I will talk through some of the data from my fieldwork in Tanzania, where I surveyed customers in Tanzania and then modeled a community level load profile. And then I compared that data from the system, and analyzed that, looking with other kind of data that I have and in the context of the community that I was working with. So some of the pictures here, so a lot of the people in this village use kerosene for lighting, which, as you can see from this picture, does not give very good light. It also causes air pollution, which causes a lot of health issues, particularly for women and children, because their ones will be generally kind of inside using this light. It also means people don't have access or have to pay a lot of money to charge their phones. They don't have TV or radio. So we're just looking at very basic access to electricity, but that can mean a lot to people. There's this data gap in the modelling between kind of how people actually use electricity and how they're kind of perceived to. So some of the previous research in this found quite large errors between people's energy use and what was actually recorded. But like I said before, these were quite siloed. So something that came up in the preliminary research that I'm going to talk about in a minute was that seasonal income could be something that affects demand. So that's a bean plant in the village I was in. They got a lot of their income from tea. And so that was one of the kind of initial questions that I thought about after my kind of first scoping stage, was whether there was going to be a seasonal trend in the demand, because people have money in some seasons when they're able to harvest and sell their crops and don't in other seasons. So a little bit more detail about what I did for my field work. So an interdisciplinary approach, so techno-economic as well as social sciences, a participatory approach. So I did a lot of workshops with the community. One of the ones at the bottom there was one of my initial focus groups, where I went around a few communities, and that was the kind of preliminary research I talked about, where I identified some potential questions to look into in more depth in future field work. So in total, I did 8 months of field work in Tanzania. So I did a lot of focus groups at the start, and then moved on to doing more interviews and observations, appliance use surveys, household diaries of what energy they were using. And also, when I got back, desk analysis of the system demand data, which I'm going to show you now. So I had that first idea of people would tell me that they had their income changed quite a lot through the year. They had the months that they had income available. So first thing I wanted to see was whether that affected the demand. So on this graph, the orange line is the average income per household per month. In the peak months, it's about $50 per month, but in the low months, people are earning only about $20 per month for a household. So this is different crops that they are able to sell at different points in the year. So tea is quite a major one, but also beans, some spices, bananas, sugarcane. Obviously, that profile of income would look different in a different village. And then the blue lines, I have a data gap here, which is 2018, just where the system wasn't connecting to the data collection software. But you can see this, the blue lines is the average peak demand per customer. on each day. And the grey lines is the average demand kind of overall. And so you're not seeing peaks at these peaks. So there's not an obvious link between payment data and the seasonal income. So each month there's a significant number of households who either don't pay at all or they underpay. So that means they're kind of self-disconnecting, which is the way this tariff works, is you pay a flat rate per month. If you pay half of that, you get electricity for half of the days, etc. So household mentioned that they have both these day-to-day benefits on their income. As you can imagine, earning $20 to $50 a month when you're paying for food, you're paying for things for schooling, you're paying for healthcare, you're paying for clothes, day-to-day life. They have those pressures as well as the seasonal variation due to harvest periods. So this lack of correlation between the demand and the seasonal income suggests that it's these day-to-day costs that have the dominant effect or the dominant impact on households not being able to afford their bills. But something where I did see a bit of a trend between this was in the change of customers, so the new connections. So the project started in 2017, this is 2018 is the first, so this kind of peak is a little bit because of the new people. But you can see in this first season in 2018, 2019, there's an increase in new customers during this harvest season. But following the first phase of field work that I did, which was March to August 2018, the company used the feedback that people had said the reason they weren't able to connect during this lower income period was because they weren't able to afford the connection fees. So the company used that feedback to implement a new way of paying connection costs, which was much more dependent on the harvest income, which they called a seasonal connection. So that was implemented in March 2020, along with the communication push, which is why you kind of see that trend of new customers from this first peak, but then later is when they implemented this new connection approach. So there's a bit of maths on this slide. I'll try and just explain briefly what it is. So the second bit of data that I looked at was the load profiles. So I compared, after comparing the total demand to the seasonal income, I created these load profiles by, for each hour, the total load was estimated. So I took the sum of each of the power of the appliances, which was taken from customer surveys and a bit of information from diaries, and then scaled that according to the number of customers connected each month. Now, I mentioned before that there is this issue of some households not connecting for some months, or not connecting, not partially connecting because they weren't able to fully pay their bill. So I considered three different values for this N. So one was the total number of customers who were connected. The next one was the number of customers who paid their bill that month. And then the next one was the number of customers who were paying at least 2/3 of their bill in a month, to see how kind of scaling according to that affected what the load profiles would look like. Some appliances aren't used for a full hour, such as things like toilets and machines. So the energy usage for those was divided by the rated power, dividing their rated power by the usage time. And for things like households, people didn't charge them every day. So again, that was scaled out across the week. So I'm just going to quickly show you. So this is what the blue line that you can see here is the data from the system. And the orange lines here that are all bunched up in January 2018. In January 2018, everyone was paying their bills. So that's those next to each other. So they get some of the shapes that you can see. There's a few kind of key aspects of that. The nighttime usage is underestimated. The peak is slightly overestimated in this one, but when we go to July 2019, if you consider all customers when scaling up the model, then you get a huge overestimation of the peak usage, which is obviously important for storage and generation capacity that you're installing, which is where the storage particularly is where a lot of the cost comes from. So this overestimation of demand leads to excess costs on the system. And then this continues to get bigger, this gap. So you can see in this one, this is at 3 and this is at 7.5. Here, this is at 6 and this is at 11. So this gap if you assume all customers are paying and are connected. But when you consider the underpayment, you can see you're modeling the peak a lot closer. So I've shown this across all of the months. So comparing, the top graph shows the average peak demand. So the orange line is the daily system peak, or the average system demand from the system data, and the bars are my modeled data. So you can see the model fits quite well in the early days for both, but when you look ahead, you can see that considering all customers, or even all the customers who are paying, you hugely overestimate your peak demand. But by considering underpayment, you get a much better idea of what the peak demand is. But then for overall usage, you get a slightly different idea of that by considering underpayment, you do still underestimate it a bit, which when you look at this, you can see is largely due to nighttime usage, which again is really important for storage, because that's when it's not sunny. So this error increases over time. So close to by with underpaying customers are taken into account. So poorer households are more likely to underpay or disconnect, and also only have demand at model times. Another feature is that this model peak is a bit earlier than the actual peak. So in Tanzania, they have times of day quite culturally specific. So if you say night time, it specifically means 7 p.m. Sorry, my phone's ringing. But actually, when it gets dark, varies not a huge amount, because Tanzania is quite near to the equator. But actually, it's more likely to be a gradual turning lights on. Then this overnight usage being underestimated. One of the reasons for this may be that another researcher had previously done some work on energy efficiency in this village, and they'd told people about how bad it was to leave your lights on at night. So one of the things might be that people didn't want to report that they were using their lights at night because they were aware it was not an efficient use of the system. They might also forget, or I might not have been, I was only speaking to 1 or 2 members of the household, and it might be that other people were turning the lights on at night. Then this little peak that you get at 9 a.m. Is a fridge peak, because some people said they just turned their fridge on at 8 p.m, but that isn't as seen in the data. So it might be because of the thermal properties of fridges, or it might also be because they didn't actually turn it on at the same time every day. So just quickly, I'm aware I've only got 30 seconds left. What does this mean? So developers need to think about how people will choose to answer these questions about demand. So although I asked people, and I talked about the nighttime peak, for example, that they might not answer because they were aware they might not be using the electricity efficiently, so they might not want to be honest. Need to consider when modelling at a project that not everyone will be able to use their desired demand. So this is, people have done willingness and ability to pay, but when it actually comes down to it day to day, people have other stresses on their income that they might choose to prioritise, like healthcare, for example, which is demonstrated by the high levels of underpayment and missed payments. So finally, there's 2 ways that this research could be interpreted. From a technical standpoint, a better understanding of this variation in demand may allow systems to be designed more efficiently, but also from a more social sciences background, is that it's not acceptable that systems have this demand, because in practice, it means that households are going out without their basic needs. So there's also a need for research into business models and kind of ways of supporting that allow households to have electricity all year round. Any questions?
Anna?
There we go.
Fantastic.
Hi, Hannah. Can you tell us a little bit more about the energy system that was being used to provide the energy in this particular study?
So it was a 48 kilowatt solar. I'm just going to try and get the information up. Sorry, my computer is now deciding to be slow. Must I just try and get the information up? So it's a 48 kilowatt solar plant with, they had a diesel backup generator, but that was, to us, not used at all really, because it was the project was basically oversubscribed, and then it had, I'm just trying to get the, I know as engineers that you'd like some numbers, so I'm just getting up the OPZS is the battery storage. I'm just trying to find out whether I've got how much, and a 50 kilovolt amp diesel generator as backup. Just trying to find the document that says how big. But basically, it's quite an overpowered system for the community. If you're looking at those, so the maximum peak was about from the system was about 8 kilowatts, and it's a 48 kilowatt peak. And the storage was, so it was 100% reliable, apart from occasional outages because someone like plugged in a DC appliance rather than AC, which would cause issues. You just leave me for a second. If there's any other questions, I'll come back and I can tell you how big the batteries are in a minute.
So where I was going was, I just wondered whether you thought there was any, whether that had any impact on how people, the end users, actually interacted with the power supply. But given that it was over-engineered, perhaps there weren't any issues, that power was always available.
Yeah, so I mean, but in speaking to people, so when they compared their electricity supply, so another paper that I've been working on was looking at tariffs. So these people pay about 50 times per unit for electricity than you would if you were connected to the grid. But there's villages just down the hill who are connected to the grid, and in rural areas they can have outages for weeks because you've got kind of out of date transmission infrastructure go to these places, and if there's any faults on those lines, it's not a priority for the TANESCO, the National Electricity Company, to fix those. So people who are connected to the national grid have these like week-long outages, but they pay about a 50th of the price. They pay 3p per unit. So yeah, but I think, because in terms of one project I visited was I didn't do my main case study, but where I visited was biomass. So I see then you've got an interaction with the community a bit more with the fuel, because they were providing rice and corn husks, mostly corn, to power it. But then there's other things those might have been used for in terms of for composting. But that project again was undersized. It was oversized, so there wasn't really that issue with demand. And then the hydro projects, obviously, where you have more of an environmental impact, but the kind of the footprint of the power plant isn't huge compared to the village. And they did good work in the village, kind of getting local people involved in the building of that and being involved in that. So they were quite in favour of the technology. It was just the cost that they were not happy with.
Fantastic. Well, thank you very much, Hannah. I can't see any more hands up at the moment, so thank you for an awesome talk there. So,
thank you.
And yes, thank Hannah again.